In this example, we're asked to find the skin friction drag on this thin equilateral triangular plate, which is immersed parallel to a 1 meter per second stream of air. So one of the first things to make a note of is the drag, the skin friction drag on this plate will act at both the side facing toward us and then the back side of the plate. Since it's a thin plate, there's kind of a front side and a back side, so we have to make sure that we account for both sides. The other thing to keep in mind is that the distance on the plate as we go downstream changes over the surface of the triangle. What I'm talking about here is, let me put in some coordinates and then you'll see what I'm talking about. So let's call this the y direction, and this is the x direction. So as we move downstream on the plate, let's say like right here, that distance for that little rectangle will of course change depending on where I am in the y direction. So let me call this distance here x, and the width in the vertical direction will be dy. It's just a small displacement in the y direction, so the area of that little rectangle will be x times dy. And because that distance changes, the drag force, the skin friction drag on that little rectangle will change as I go from this upper corner all the way to down here. So I'm going to have to find the skin friction drag on each one of those little rectangles and then add them all together to get my total skin friction drag on one side of the triangle. Now, since the triangle is symmetric from top to bottom, I'm going to only worry about the top half of the plate. So I'll find the total skin friction drag on the top half of the plate, multiply it by 2 to give me the total skin friction drag on one face of the plate, and then multiply that by 2 to get it on the front and back faces. So one of the first things I need to do is figure out what that distance x is for each one of these little rectangles. Now, in order to do that, what I'm going to do is have to find the equation of this line that describes the sort of the angle of the plate there. Let's call this angle here theta. And because it's an equilateral triangle, I know that theta is going to be 30 degrees because the total angle of each of these corners will be 60 degrees since it's equilateral. Now, this surface, this edge of the triangular plate is a straight line, so I can just write down the equation of a line here. So I'll have the slope. You know, y, what I'm going to do is write down y equals mx plus b, just the standard equation for a line. So m is the slope, and here it'll be a minus tangent theta times x plus an intercept, and it'll be 1/2 L, where this is L here. So 1/2 L just gets me this part. So L here is 2 meters. And since I'm trying to find the area, you know, the x in terms of y here, because ultimately I'm going to have to integrate with respect to y, so it's best to just rewrite this as, just kind of rearrange this equation so I have x in terms of y. So this will be y minus 1/2 L divided by minus tangent of theta, or 1/2 L minus y all over tangent of theta. And by the way, just to get the maximum distance, let's call this x max here, I can go ahead and plug in y is equal to 0 right down here, plug in my theta, plug in my L, and what you'll find is that x max comes out to be 1.73 meters. We're going to refer back to that number in just a moment. All right, so we've kind of set up the geometry here. Now let's go ahead and start calculating the skin friction drag. In order to find the skin friction drag, I need to know whether these boundary layers, you know, the boundary layer over these little rectangles is either laminar or turbulent or some combination of both. So I'm going to calculate the Reynolds number on these. And in fact, actually what I'm going to do is I'm going to calculate the distance. At what distance does the boundary layer go from being laminar to turbulent? So I'm going to find that critical distance. I'm going to call that x critical. And that'll be based on the Reynolds number when the Reynolds number is equal to 500,000. We know that that's the transition Reynolds number between laminar and turbulent flow. So I'm going to find that critical x distance at which we go from laminar to turbulent flow. So if I plug in u is equal to 1 meter per second, the u here is this velocity leading into the plate. It's 1 meter per second. kinematic viscosity for air is 1.5 times 10 to the minus, I believe it's 10 to the minus 5. Let me just double check my numbers here. Yeah, 10 to the minus 5 square meters per second. If I plug those numbers in, then I'll get the critical distance at which I go from laminar to turbulent flow is 7.5 meters. And if you compare these two, what you'll see is that we're well below that for all of our little rectangular plates. So we're going to have a laminar boundary layer over that entire triangular plate. So that means when I use my boundary layer correlations, I'm going to use the laminar boundary layer correlations. So let's go ahead and calculate the drag on that little rectangular strip. So the little bit of drag force due to skin friction on this little rectangular strip up here will be the drag coefficient, and specifically this will be a laminar drag coefficient. It'll be our Blasius drag coefficient since we're dealing with boundary layer flow over a flat plate. It'll be that multiplied by the dynamic pressure based on the free stream speed times the area of that little plate, which is x times dy. And then let's go ahead and expand that out. Let me put in the drag coefficient for the Blasius boundary layer. That's 1.328 divided by the Reynolds number based on the distance from the leading edge to the trailing edge, raised to the 1/2 times 1/2 rho u squared times x times dy, where the Reynolds number is just the free stream velocity times x divided by the kinematic viscosity. And x, again, is just the distance of that little rectangular strip. I can go ahead and simplify that a little bit. Let me just go ahead and write out what the Reynolds number that is there and kind of simplify everything down. If you do all that, this will be 0.664 times the square root of the kinematic viscosity times the density times the free stream velocity raised to the 3/2 power times x raised to the 1/2 power times dy. So that's the little bit of drag force on that one little rectangular strip. So now I know that I have actually a bunch of rectangular strips. So to find the total drag on, now this is just the, let me write this out and then I'll explain it. So to find the total drag on just this upper triangle up here, I'll integrate as y goes from 0 to 1/2 L. And then I'll integrate all those little bits of drag force. So let me write that out. Right? And that'll give me the drag on just this kind of circled region up here, just the upper triangular plate. Now remember, I have the lower triangular plate too, so I want to multiply that by 2 to get the drag on one face of this equilateral triangle. And then I'm going to multiply it by 2 again to give me the front and back faces. So this first 2 is kind of upper and lower, and the second 2 is like front and back. Okay? Now the other thing that I have to do, to be careful of when I do this integral, is you'll notice that I'm integrating with respect to y. So we know that x is actually a function of y, so we should really substitute in for x. Remember that x is equal to 1/2 L minus y all over tangent theta. So we should substitute in for x to make sure it's in terms of y when we do our integral. And if you go ahead and do that integral, I won't go through the math of that. That's kind of tedious and it's not really necessary. I'm sure you can figure it out, give it enough time. But if we do that math, this will come out to be 0.626 times the density times u times L raised to the 3/2 times the square root of the kinematic viscosity over the tangent of theta. So that's what the drag comes out to be. And then when you plug the numbers in for that, we'll get the drag is 1.1 times 10 to the minus 2 newtons. Using all the various numbers. The density, by the way, the density for air, I don't think I gave you that earlier, but that'll just be 1.23 kilograms per cubic meters. I think all of the other parameters I gave you earlier in the problem. So that's how you find the drag on this triangular plate. So a couple of things just to recap. First of all, we realized that the length of each of those rectangular strips up here changes, so we had to figure out what the length of each strip was. That was what this expression came out to be. Then we checked to see whether the boundary layers were laminar or turbulent. We found that in all cases it'll all be laminar. Then we found the drag on one little rectangular strip that's given right here. It's just the drag coefficient times the dynamic pressure times the area of that little strip. To get the drag coefficient, we recognize that, well, since it's a laminar boundary layer, it'll be the Blasius relations for laminar boundary layers. So we looked up the drag coefficient for a laminar Blasius style boundary layer. And that gave us this point, and then we went ahead and integrated that over the whole upper part of that triangular plate. So that's what this part is, keeping in mind that x is a function of y, so we had to substitute in for there. And then we recognized we have an upper and lower surface, as well as a front and back surface. And then at that point, some math and plugging in numbers. All right, we'll go ahead and end.